Have you ever stood outside and looked up at the stars? On a clear night, the sky glitters with countless points of light, each a distant sun. Our solar system is just one among billions, perhaps trillions of systems scattered throughout a vast expanse we call the Milky Way. As we gaze upward, we feel a sense of wonder and insignificance all at once. How could we possibly comprehend such immensity? Our minds rebel against the notion of infinite space and time. So we imagine an edge to the universe, a boundary that limits the boundless. But even knowing the size of the universe doesn't satisfy our curiosity. We want to know where it came from and where it's going. It turns out the beginning and end of the universe are intimately connected, because for as long as humanity has looked upward, we have asked, where did the universe come from? But hidden within that question is another, just as profound. Where is it going? Cosmology, the study of the universe as a whole, tells us that the universe has a beginning, the Big Bang. But what about its end? Will everything collapse in fire, freeze in darkness, or be torn apart by forces beyond comprehension? The first clue to understanding the fate of the universe comes from a force we encounter every day, but rarely connect to cosmic time: entropy. When we think of entropy, we usually consider disorder. Think about your bedroom. It's a pretty good example of high entropy. There's also natural entropy in the universe. Stars form from collapsing clouds of gas. Galaxies form from collapsing clouds of stars. Black holes form from collapsing clouds of matter. In each case, something forms because particles have more energy when they are spread apart than when they are close together. And so the most likely fate of the universe is heat death. As the most energetic regions of the universe expand and cool, the amount of order in the universe will decrease. Eventually, stars will die out, galaxies will drift farther and farther apart, and the universe will grow silent, cold, and empty. But there are other possibilities. As Albert Einstein showed, mass is really another form of energy. And according to the equivalence principle, gravity should act on this energy as if it were really there. To explain how gravity works near black holes, physicists developed the concept of space-time. Space and time intertwined in a flexible fabric warped by the presence of mass. If the entire universe is a kind of hyperdimensional black hole, then its interior would resemble the inside of a black hole. And at the center of that would be a singularity, a region of infinite density and temperature. So as the universe collapses, everything would be pulled together and crushed into an infinitely hot, dense point. If we take this idea to its logical extreme, we get the heat death scenario. After the big crunch, the universe would bounce back into a new Big Bang and start over again. This is called the Big Bounce theory. It has some appeal because it sidesteps the issue of the initial singularity. After all, we don't actually know what happened at the beginning of the universe. But it doesn't sidestep the problem for long. Any theory describing the behavior of the universe must account for the abundance of matter over antimatter, as well as the nearly perfect smoothness of the universe on large scales. And these features are difficult to reconcile with the Big Bounce. For one thing, the core of the collapsing universe would heat up to unimaginable temperatures, and when it exploded back outward, the high-energy particles would quickly annihilate, leaving behind only photons and neutrinos. There wouldn't be enough matter left over to form stars and galaxies. But there's another possibility, a fate for the universe that is truly terrifying. Imagine standing under a night sky millions of years from now. Stars above, once countless and brilliant, have begun to vanish. The familiar constellations are gone. Galaxies themselves drift farther and farther apart. When as the glow of distant suns fades, you see that the sky is not filled with stars, but with an encroaching darkness. You are witnessing the heat death of the universe, and it is silent. No new stars will ever form. The universe is dark. The earth is dead. There's fair other theories about the fate of the universe, but none are very compelling. Some cosmologists speculate that the universe will continue expanding forever. Others believe the expansion will slow down due to the gravitational effects of matter. But that seems unlikely since we can already see that the expansion of the universe is speeding up. Still others speculate that the universe will eventually stop expanding and then begin to contract. But if that were the case, we would already be feeling the gravitational pull of the distant universe, and we aren't. For now, the fact is, no one knows what the ultimate fate of the universe will be. and perhaps we are too primitive to understand such mysteries. But we can say this: whatever happens, it won't be easy to survive. The ultimate fate of the universe is inevitable. One day, everything that can happen will have happened. The only question is when. A few trillion years from now, the sun will expand into a red giant engulfing Earth. But it's not all doom and gloom. It might be long gone. Or if things go well, we'll have become a spacefaring species and left the solar system long ago. But whether we're around to see it or not, this is just the beginning of the story. What happens next depends on the nature of our universe. Is it rich with matter, dominated by dark energy, or held together by dark matter? Well, the future looks pretty bleak either way. In this universe, stars will burn out one by one, black holes will evaporate, and the cosmic microwave background will be the only thing left. For billions of years, the heat death of the universe is often described as a heat death. But it's actually a misnomer, because it doesn't involve anything fiery. Instead, it's a slow fading into nothingness. Sounds depressing, right? Well, fortunately, there are a couple of more interesting ways the universe could end, depending on how much stuff is in it. First, let's consider the simplest possible case: a universe containing nothing but a single, non-rotating black hole. This may seem boring, but it actually gives us a glimpse of what happens under extreme conditions. As we know, nothing can escape a black hole, not even light. So once everything falls in, we're left in total darkness. However, Stephen Hawking showed that black holes aren't entirely black. They emit a thermal radiation known as Hawking radiation, which comes from quantum effects near the edge of the black hole horizon. This means black holes slowly lose mass and evaporate over time. In fact, the more massive the black hole, the slower it evaporates. This has profound implications for our universe. Since all the mass of our universe is concentrated in black holes, the larger these black holes, the longer they live. Eventually, however, they too must die. But in the meantime, as they evaporate, they'll create a lot of Hawking radiation. This radiation will heat up the universe, increasing the entropy. In fact, this process would eventually lead to a state known as thermality, where the entire universe is filled with Hawking radiation. But how big does the universe need to be for this to happen? We can estimate the age of our universe today to be about 13.8 billion years old. The size of the observable universe is about 94 billion light-years in diameter. The largest black hole we know of today is named Phoenix and has a diameter of 465 billion kilometers. Using these numbers, we can calculate the amount of time it would take for Hawking radiation to heat up the entire universe to a temperature of 10 trillion Kelvin. Turns out, it would take roughly 10 to the power of 10 to the power of 10 seconds, also known as a googol to the second power. That's an insanely large number. If we compare this to the estimated age of the universe, we find that it would take at least 10 to the power of 10 times the current age of the universe for the universe to heat up enough to make a significant change. And even then, the change wouldn't be that significant. However, the issue is that we don't know the exact value of this quantity. The best current estimates suggest it would require a goggle time for the universe to heat, up to 10 to the power of 32 Kelvin. Another option is if the universe contained no matter at all, only radiation. This may seem weird, but it turns out that it's physically possible for a universe to exist without matter. There's no evidence for this in our observable universe, but it's a mathematically valid solution to the equations of physics. This type of universe is known as a radiation-dominated universe. Radiation makes up most of the energy density of this universe. Examples of radiation include light, X-rays, radio waves, and any other form of electromagnetic radiation. If our universe had started out as a radiation-dominated universe, we would have seen a drastically different set of physical processes taking place. Most importantly, the rate of expansion would have been much faster. This is because the rate of expansion of the universe is determined by the amount of matter and energy present. More matter means slower expansion, while more energy means faster expansion. Since there's no matter in this universe, the expansion would have been very rapid. As the universe expanded, the wavelength of the radiation would have stretched, causing it to cool. The result would have been a universe filled with low-frequency radio waves. Today, this type of universe would be vastly different from our own. The lack of matter would have prevented the formation of stars, galaxies, and planets. As we know, stars and galaxies are made of matter. Without matter, there would be nothing for gravity to act on, meaning no stars, no galaxies, no planets. Just a cold, dark void of low-frequency radio waves. This scenario illustrates how important matter is to the universe as we know it. The presence of matter allowed for the formation of stars, galaxies, and planets, ultimately leading to the emergence of life. However, the radiation-dominated universe scenario highlights the importance of understanding the fundamental laws of physics and the various possible solutions they allow. By exploring these different scenarios, we can gain a deeper understanding of our own universe and the amazing features that make it unique. Now, let's imagine a scenario where the universe contains both matter and radiation, but it has a twist. The radiation has a negative pressure. You heard that right? Negative pressure. Normally, pressure is always positive. When you press your hand against a wall, the wall exerts an equal and opposite pressure back on your hand. However, there are some situations where the pressure can be negative. For example, in certain types of nuclear reactions. The pressure can be negative due to the Casimir effect, which arises from quantum fluctuations in a vacuum. In fact, there are several observations that suggest the existence of such negative pressure, including the accelerated expansion of the universe and the fine-tuned constant of dark energy. If our universe had started out with negative pressure radiation, the expansion of the universe would have been even faster than before. As the universe expanded, the wavelength of the radiation would have stretched. But the negative pressure would have caused the energy density to increase rather than decrease. The result would have been a universe filled with high-energy gamma rays and X-rays. This scenario is similar to our own universe in some ways, but with some important differences. The higher energy radiation would have made it difficult for matter to clump together and form structures like stars and galaxies. It would also have made the early universe opaque, since the high-energy radiation would have been unable to travel very far before being absorbed by matter. This opacity would have prevented the formation of large-scale structures like the cosmic web. Additionally, the negative pressure radiation would have exerted a strong outward force, making it hard for matter to collapse and form dense objects like neutron stars and black holes. But wait, there's more. If the amount of negative pressure radiation was just right, the expansion of the universe would have increased exponentially. This is known as the Big Rip scenario. In this scenario, the negative pressure radiation would have dominated the energy budget of the universe. The expansion of the universe would have increased exponentially, tearing apart everything in its path. Even atoms and nuclei would have been ripped apart. This doomsday scenario might sound terrifying, but it's not all bad news. It gives scientists a chance to test their theories about the nature of the universe and the fundamental laws of physics. By studying the properties of radiation and the behavior of matter under extreme conditions, scientists can better understand the workings of the universe and our place in it. So while the heat death of the universe may not be the most exciting topic, it's an important one. It allows us to explore the limits of our understanding and pushes us to discover new knowledge about the amazing world we live in. Here's something we keep coming back to on this channel. How did we get here? By here, I mean pretty much anywhere in the vastness of the universe. But if you want to know how we got here, there are some very important places you need to visit. Like here, for example, inside of a star like our Sun. Here, literally hundreds of millions of miles below the surface, is where the magic happens. Hydrogen atoms are converted to helium, and in that process, photons are released, and it's that light that allows us to see our Sun in the first place. And it's that process that gives our planet the energy it needs to exist. But that magic doesn't last forever. One day the hydrogen fuel runs out, and when that happens, the outer layers of the star are cast off into space, and what remains is called a white dwarf. Now, white dwarfs aren't quite dead. They still have plenty of energy left over from when they were stars. They just can't make more. So the question is, what happens next? Well, according to the laws of thermodynamics, all the energy in the universe is spread out evenly, and eventually our white dwarfs will run out of energy and begin to cool. But do they just fade away into the blackness of space? Do black dwarfs fade away? What happens then? Well, join me and let's find out. Welcome to the channel. First things first, let's start with a refresher on white dwarfs because they're actually pretty incredible objects. As I mentioned earlier, they're the remnants of low to medium mass stars after they've gone through their entire supply of nuclear fuel. The core collapses in on itself under the pressure of its own gravity until it reaches a point where it's incredibly dense. Imagine squeezing the entire mass of the sun down to the size of Earth. That's what we call a white dwarf. White dwarfs can actually have a wide range of masses, typically between half and 1.4 times the mass of the sun. They also have a pretty wide range of radii, which means that they come in a variety of sizes as well. However, their densities are always pretty similar, and I mean incredibly dense. Even a teaspoon of a white dwarf's material could weigh several thousand pounds. And while a white dwarf is still glowing from the energy produced during its life as a star, it doesn't produce any new energy. Instead, they radiate the heat from their hot and dense cores into space. Now, since white dwarfs are no longer generating energy, they begin to cool. And this cooling process is incredibly slow. We're talking thousands of trillions of years slow. However, eventually, they will cool enough to no longer be visible to us. And when that happens, they become what we call black dwarfs. Now black dwarfs are essentially white dwarfs that have cooled down so much that they're no longer emitting any visible light. Essentially, they're the end stage of a low to medium mass star. And if the star was in a binary system and it had a white dwarf companion, it might transfer some of its mass to that white dwarf. But if the star was single like our sun, then it will just drift through the universe as an invisible black dwarf. But black dwarfs aren't quite dead either. They still have a lot of thermal energy left over from when they were stars. It's just that they can't do anything with it. They're stuck in a state of maximum entropy. Everything is spread out and there's no gradient left to drive any energy production. So what happens next? Well, that depends on a few factors, including the mass of the black dwarf. For example, if it has more than about 2.5 times the mass of Jupiter, it will collapse and become what we call a neutron star. Neutron stars are incredibly dense and they're also incredibly hot. And as they cool down, they emit radiation that can be detected by modern telescopes. However, most black dwarfs won't be massive enough to collapse into neutron stars. Instead, they'll just continue to cool. In fact, black dwarfs might be able to cool so efficiently that they begin to undergo a process known as proton decay. Now, proton decay is a hypothetical process in which protons break down into neutrons, electrons, and positrons. It's not something that happens in our universe, at least not that we know of. But it is something that could happen if the laws of physics allowed for it. Now, proton decay would essentially break down the black dwarf from the inside out, turning it into mostly subatomic particles. The upshot would be that a black dwarf that underwent proton decay would be basically gone. And if it had any nearby white dwarfs, it could cause them to decay as well. However, there's no consensus on whether or not proton decay is possible. And if it is, we don't know how likely it is to occur. So we can't say for sure what will happen to black dwarfs in the long run. And that brings us to the ultimate fate of all black dwarfs, black holes. Now this is where things get really interesting. You see, black dwarfs may not be able to generate any new energy, but they can interact with other objects in space. And that includes other black dwarfs. If a black dwarf were to pass close enough to another black dwarf, their gravitational fields could interact, causing them to merge together. And if two black dwarfs merge together, the resulting object would be more massive than either of the original black dwarfs. That means that it would be more massive than the Chandrasekhar limit, which is the maximum mass of a white dwarf. And if an object is more massive than the Chandrasekhar limit, it can collapse into a black hole. So essentially, two black dwarfs could merge together and collapse into a black hole. However, this isn't something that would happen overnight. It would take thousands of years for the black dwarfs to come close, enough together for their gravitational fields to interact, and even longer for them to merge and collapse into a black hole. But it is something that could happen, and it does happen. In fact, scientists think that many of the supermassive black holes at the centers of galaxies formed this way, by gradually consuming smaller black holes. So while it might not be the most likely outcome, it is possible that many of the black holes we see today started out as black dwarfs. The real question is, will all black dwarfs turn into black holes? Will anything stop them? Well, maybe. Some physicists believe that black holes aren't truly black holes at all, that they have a radius known as the Schwarzschild radius within which nothing can escape their gravitational pull, not even light. But beyond that radius, they believe there's a region known as the ergosphere, where space is dragged around by the black hole's rotation. And within the ergosphere, it's theoretically possible for objects to escape the black hole's gravitational pull. If this is true, then black holes might not be able to grow forever. Eventually, they would reach a maximum size determined by the speed of light and their own rotation. That means that they wouldn't be able to consume all the black dwarfs in the universe. Instead, there would be some black dwarfs left over. So in a universe dominated by black dwarfs and black holes, the big question is, what will happen to those black dwarfs that aren't consumed by black holes? Well, that's a tough question to answer. You don't really know what would happen to them. You don't know what will happen to black holes, let alone black dwarfs. But we do know that they would be frozen solid and completely dark. The only way to see them would be by detecting the tiny amounts of radiation that manage to escape their surfaces.
Ouch.
And by tiny, I mean incredibly tiny. It's hard to imagine a universe that's completely dark. But it's also hard to imagine a universe that's dominated by giant black holes. We don't know what will happen to the black dwarfs, or if they'll ever be consumed by black holes. But we do know that the universe will be a very different place without stars. It'll be a place without light, without heat, and without energy. It'll be a place of complete darkness and utter silence. In the grand sweep of the cosmos, our lives are fleeting. Yet in the grand sweep of time, our age is unprecedented. Never before have we had such knowledge of the universe or such power to explore it. From the smallest quantum to the largest galaxy cluster, we are revealing the secrets of reality. But there's a twist in this story. As we probe deeper, we find ourselves hurtling toward an endpoint we never expected. And what we discover along the way just might change everything. The objects we've seen, white dwarfs, black dwarfs, and black holes, show us what happens to stars. But to understand the fate of the universe itself, we must zoom out. What will happen not to a single star, but to the cosmos as a whole? This is one of the greatest open questions in physics, and scientists have developed three major scenarios: heat death, the big crunch, and the big rip. Let's start with the first two, which are essentially opposite in their predictions. First, the heat death, also called the big freeze. In this model, the expansion of the universe continues forever, powered by dark energy. Stars exhaust their fuel. Galaxies drift apart, vanishing beyond each other's horizons. In the far, far future, only white dwarfs and neutron stars remain, remnants of dead stars that have long since cooled. Eventually, even black holes evaporate. All that's left is a vast, thin soup of radiation and subatomic particles, spread so evenly that no energy differences remain. Without differences in temperature or density, no processes can occur. No stars ignite, no life can survive, no structures can form. The universe becomes a uniform, silent void. It is a death not of violence, but of stillness, the final consequence of the second law of thermodynamics. For many cosmologists, this is the most likely fate, but not all agree. What if dark energy, instead of accelerating expansion forever, were to weaken or even reverse? In that case, gravity could then take over, pulling galaxies back together. Over trillions of years, the expansion would slow, halt, and reverse. Galaxies would collide. Stars and black holes would collapse into each other. Temperatures would rise again as the universe shrinks. In the final moments, everything would compress into an unimaginably dense state, a mirror image of the Big Bang. This cosmic rebirth might even suggest the universe is cyclical, endlessly expanding and contracting. Some theorists see echoes of this possibility in models of bouncing universes. However, current evidence strongly favors acceleration, not collapse. Dark energy seems to be growing stronger with time, not weaker. That makes the heat death more likely. If you found this interesting, please stay tuned. Now, while these two scenarios are rooted in scientific speculation, the third option leans heavily into science fiction. It's known as the Big Rip. In this model, dark energy is not constant. Instead, it grows stronger with time. And if it grows without limit, the results are devastating. First, galaxies are pulled away from each other at ever-increasing speeds. Then gravity itself weakens under the strain. Stars are torn from galaxies. Planets are torn from stars. Eventually, even atoms are ripped apart. At the final instant, perhaps 20 to 30 billion years from now, depending on dark energy's behavior, the very fabric of space-time is shredded. Unlike the heat death, which takes place across unimaginable timescales, The Big Rip ends the universe in a relatively short and violent catastrophe. So which of these scenarios is correct? The answer depends on the true nature of dark energy, the mysterious force driving cosmic acceleration. If dark energy is constant, the universe ends in heat death. If dark energy decreases, the universe may collapse in a big crunch. If dark energy increases without limit, the universe faces a big rip. The challenge is that dark energy makes up about 70% of the universe. Yet we know almost nothing about it. We cannot say with certainty whether it is constant, fading, or growing. In other words, the fate of everything depends on the biggest mystery in modern cosmology. But we have another problem. We're trying to use our human brains to understand concepts that are nearly impossible to fathom. To wrap our minds around the idea of a cooling, expanding universe, we need to think about the passage of time in multiples of billions of years. When we talk about how old the universe is, we're talking about roughly 13.8 billion years. When we discuss the timeline for the heat death, we're talking about times longer than that. How do you conceptualize something that blows the mind just thinking about the numbers involved? There are various ways people try to cope with this cognitive dissonance. Some use analogies. They imagine the universe as a hockey puck gliding across an icy plain or a balloon being slowly deflated. Others use visualization. They imagine themselves zooming out to the scale of the entire universe and watching its evolution over billions of years. Still others use intuition. They reason that since the universe has been expanding for billions of years, it should continue to expand indefinitely. But none of these methods are perfect. After all, the universe is not a physical object that we can hold in our hands, or a mathematical equation that we can manipulate on a chalkboard. It is something vastly more complex and mysterious. To truly understand the heat death, we need to confront the limits of our own minds. We need to acknowledge that there are some things we just can't know, some experiences we can't have, some concepts we can't fully grasp. We must accept the humbling realization that the universe is too big, too old, and too strange for us to ever truly comprehend. Yet despite the limits of our understanding, we press on. We push deeper and deeper into the mysteries of the cosmos, searching for answers to the biggest questions of all. Why are we here? Where did everything come from? And what happens after the heat death? For in the relentless march of progress, it is not enough to simply accept the unknown. We must strive to understand. While the fate of the universe is shrouded in mystery, the fate of our own world is clear. The sun will run out of nuclear fuel in about 5 billion years, triggering a chain of events that will likely spell the end for life as we know it. And while it may seem hard to imagine anything ending our run in the cosmos, there is precedent much closer to home. About 4.5 billion years ago, the young Earth was struck by a Mars-sized planet, delivering a cataclysmic blow that rearranged the planet's surface and sent debris into orbit. This event, now known as the Late Heavy Bombardment, dramatically reshaped our planet and may have played a crucial role in its early development. But it was just one in a series of chaotic events that have shaped the Earth throughout its history. Supercontinent cycles, mass extinctions, asteroid impacts, volcanic eruptions, ice ages, warming periods, the list goes on. Our planet's history is a testament to the dramatic and unpredictable changes that can occur over time. And yet life has found a way to not only survive but thrive through it all. But here's the thing. All of this is just a tiny fraction of what our planet has experienced over its 4.5 billion year lifespan. And compared to the vastness of the universe, our little blue dot is just a blip in time. The Earth's story is really just a small chapter in the grand narrative of cosmic existence. And that means that the dramatic events that have shaped our world are just a tiny preview of what is to come. Whether it's the slow, steady march toward the heat death, or the sudden violent end brought on by the Big Rip, the fate of the universe hangs in the balance. And while we may not be able to predict exactly what will happen, we can be sure that nothing will ever be the same. The universe is changing, expanding, evolving, and we are along for the ride. So as we look up at the stars and contemplate the mysteries of the cosmos, let us remember that we are not just observers. We are participants in an epic story that has been unfolding for billions of years. And who knows what new chapters await us in the vast expanse of time? Maybe we will witness the birth of new stars or the discovery of alien worlds. Perhaps we will uncover the secrets of dark energy or the origin of the universe. Or maybe we will face challenges that test our ingenuity and resilience. The future is unwritten, but one thing is certain. It will be filled with wonder, excitement, and endless possibilities. So let us embrace the unknown and all the adventures that await us in the great cosmic journey. But for now, we can say this. The universe may have a destiny that lies beyond our understanding. But our story is just beginning. You might think that trillions or quadrillions of years is a pretty long time. It's like the age of the universe, 13.8 billion years. Or its expected size at the heat death, a mind-boggling 10 to the 100 to the 100 years. In comparison, the story of Earth seems almost immediate. And yet the story of our world will end soon, measured not in cosmic eternity, but in billions of years. The fate of our world is tied to the life cycle of a single star, the Sun. And right now the Sun is about 4.6 billion years old. Halfway through its stable main sequence phase, steadily converting hydrogen to helium in its core. But in another 5 billion years, this balance will tip. When hydrogen in the Sun's core runs low, fusion will slow and the core will contract under gravity while the outer layers expand. The Sun will swell into a red giant, hundreds of times larger than today, engulfing Mercury and Venus and perhaps Earth whole. Even if our planet survives, it will not remain habitable. Temperatures on Earth's surface will soar. Oceans will boil away and the atmosphere will escape into space. Long before the Sun becomes a red giant, though, perhaps within just 1 to 2 billion years, rising solar brightness will make Earth too hot for liquid water, ending complex life. In other words, Earth's habitability is not eternal. Our planet has an expiration date, one that is already stamped on the face of the Sun. In 5 billion years, the Sun will reach its half-life, marking the beginning of the end for our solar system, and for us. When the Sun does become a red giant, though, it will mark only a brief interlude between two phases of stellar life. The red giant phase will last only a short time in cosmic terms, a mere few million years. Eventually, the Sun will shed its outer layers into space, creating a glowing planetary nebula. What remains will be a white-hot core, a white dwarf, no larger than Earth but half the Sun's mass. This ember will glow for trillions of years before cooling into a black dwarf. Thus the Sun itself will follow the same destiny as other stars of its size. Not a supernova, not a black hole, but a slow fade into darkness. But what about Earth? If the Sun expands enough, Earth may be engulfed directly, melted and destroyed in the stellar atmosphere. If not, Earth will become a barren, scorched rock, orbiting a dying white dwarf under a sky stripped of planets and stars. We may have a few billion years to turn Earth into a spacefaring civilization, colonize other solar systems, and maybe even find other worlds that are hospitable to life. Or maybe we'll be so preoccupied with staving off the end of our own world that we woe and have time to look up and see the opportunities all around us. Over yet longer timescales, gravitational interactions may eject Earth from the solar system entirely, casting it adrift as a rogue planet. In the degenerate era, it could wander for eternity through the dark, until perhaps colliding with another object or being captured by a black hole. Either way, Earth as a living world will not survive beyond the Sun's middle and final ages. We keep talking about extending the duration of human civilization, but we don't have infinite time. It's easy to forget that the Sun, like everything else in the universe, is slowly dying. It's going to die completely in a few billion years. But for now, the Sun is shining brightly in the sky, giving us light and warmth. So let's enjoy it while we can, because it won't last forever. On a clear night, there's nothing like gazing up at the stars and feeling very, very small. But even from our limited vantage point on this little blue dot, we can see that the universe doesn't stay still. Galaxies spin and fly apart. Stars explode and fade away. And over billions of years, the universe will continue changing in ways that are both beautiful and terrifying. And yet, despite the immensity of those changes, some feel oddly immediate. For example, in 100 million years or so, Earth won't be habitable anymore. Humanity might have gone interstellar by then, but if not, evolution will probably take out the X factor. From our standpoint, these changes feel almost unimaginably far off. Civilizations rise and fall in thousands of years, not billions. Yet Earth's long-term fate reminds us that our species cannot remain here forever. If intelligent life, human or otherwise, hopes to outlast the sun, it will need to move outward. To other planets, other stars, perhaps even other galaxies. This possibility transforms the end of Earth. From a tragic inevitability into a challenge. Can intelligence survive the death of its home world? Can technology outrun entropy, expansion, and stellar death? But even if life leaves Earth, it cannot escape the broader fate of the universe. In about 4 to 5 billion years, the Andromeda Galaxy is on a collision course with the Milky Way. Set to merge with our galaxy around the same time, the sun becomes a red giant. Our descendants, or whatever intelligent life exists, then may witness the night sky fill with the light of colliding galaxies. But beyond that, as expansion accelerates, all galaxies outside our local group will eventually slip beyond the cosmic horizon. The future inhabitants of Earth's region of space will be cut off from the wider universe, living in an island of stars surrounded by eternal dark. When we think of the end of the universe, Earth plays only a small role. Yet its story is a microcosm of the cosmic pattern. Birth from the ashes of stars, flourishing under a stable sun, eventual decline into lifelessness. In that sense, Earth's fate mirrors the fate of the cosmos itself, a journey from fire to silence. But humanity has always sought meaning beyond destruction. Across cultures and centuries, people have wondered about doomsday not just in religious myths, but in science itself. So let's turn now to the human gaze. How our species has imagined, calculated, and sometimes feared the end of all things. Our modern scientific ideas about the heat death of the universe go back to the 19th century, when the laws of thermodynamics first revealed that entropy wins every time. That wasn't the first nor the last word on the subject. Doomsday predictions have been a fixture of human culture for thousands of years. Some tie these narratives to religious texts and prophecies, while others approach the topic more scientifically. For example, in 1612, an English writer named Thomas Stoughton published The Whole Duty of Man, which outlined, among other things, a Christian's guide to avoiding damnation. According to Houghton, the end of the world would come in 4 steps. First, a great fire would rain down from heaven. Then floods would cover the earth. Next, rocks and dust would blot out the sun. And finally, the whole earth would be consumed by darkness. While that particular prediction didn't pan out, the idea of a scientifically grounded doomsday scenario stuck around. In the 1800s, writers like Lord Kelvin and others began calculating just how old the Earth could possibly be. After all, if the planet had a beginning, it must also have an end. One calculation from Kelvin in 1862 suggested that the Earth would run out of coal in 1,000 million years, dooming humanity along with it. In reality, we have a lot more than 1,000 million years left. But it's worth pointing out that even though our estimates of Earth's age were way off, our intuition about our planet's fragility in the face of cosmic forces was spot on. As the universe expands, it cools. Stars will die out one by one until every single one goes out, leaving behind only black holes, dead stars, and planets. In the end, only darkness will remain. But maybe there's something poetic about that, because as we look out into the darkness, we glimpse what we might become. Not nothing, but also not anything. We are here today, but our story began long before we first appeared. The sun, the earth, the very building blocks of life itself arose from the dust of dead stars. And someday, our species, too, will return to the cosmos, enriching the material from which new life, new worlds, and new stories can arise. The question of how the universe might end has been on humanity's mind for as long as we have looked to the stars and seen them as more than just pinpricks of light. Our earliest ancestors likely saw comets blazing across the night sky and linked their appearance to significant events here on Earth. Soon, people started seeing omens in the stars. Astrology was born. And while astrology may not be much more than fortune-telling today, it was once the cutting edge of humanity's understanding of the cosmos. As we developed more sophisticated instruments to peer deeper into space, we continued to find omens. In the 1920s, Edwin Hubble discovered that the universe itself is expanding. Suddenly, there was evidence that our universe had a beginning, and with that, a potential end. We learned that nearly everything in the universe was moving away from us. Stars were flung across the night sky like sparks from some immense explosion, flying apart in every direction. The Big Bang was born, and with that theory came the heat death of the universe, an ending as lonely and cold as it sounds. But maybe the universe won't end at all. Maybe it will simply change, growing ever more strange until it's unrecognizable from the universe we live in today. These possibilities have captured the imaginations of scientists, philosophers, and writers for centuries. So how will it all end? Let's take a look at a few doomsday theories, both old and new. First, let's talk about the heat death of the universe. You may have heard this one before. In the 19th century, physicists were working out the implications of what they now knew were the fundamental rules of the universe. They were asking what would happen if those rules were followed to their logical conclusions. One such conclusion was the second law of thermodynamics. It states entropy wins every time. Entropy basically is a measure of disorder. Imagine a nice warm cup of tea. Over time, the heat will spread from the tea into the air until the tea is cold and the air is slightly warmer. You can't spontaneously reverse the process. You can't unmix the hot and cold, no matter how much you want that tea to be hot again. Physics says no. Eventually, the entire universe will reach maximum entropy. Everything will be evenly distributed. Nothing will be moving relative to anything else. There will be no more stars, no more planets, no more galaxies, no more black holes, no more nothing. Just a uniform distribution of matter and radiation. All the action is over. This is heat death, and it's kind of boring. It's also unlikely to happen, at least according to physicists. See, it depends on the amount of matter and energy in the universe. If there's an infinite amount, then entropy will keep winning, pushing the universe toward heat death. But if there's a finite amount, then gravity will start to win over time. And now we're talking about the heat death of the universe. You could be in the middle of the big crunch right now and not even know it. Here's how it goes. In the far future, most of the matter in the universe will have collapsed into gigantic black holes. Galaxies will have merged into a few massive galactic cores. Stars will have long since burned out, leaving behind only white dwarfs and neutron stars. Everything would be drawn together by gravity, collapsing into a single, infinitely dense singularity. This is called the heat death of the universe. It's also unlikely to happen, at least according to physicists. See, our universe isn't infinitely large. We can see for about 94 billion light-years in any direction. It's the size of the observable universe, and it's finite. That means there's a limit to how much gravity can pull things together. Yes. All the matter in the universe will eventually collapse into a single black hole, but not everything. Dark energy will keep repelling the collapse, preventing a heat death. Dark energy is everywhere, and it seems to be getting stronger. That means the expansion of the universe will eventually overcome gravity entirely. Every galaxy will drift away from every other galaxy, and stars will burn out one by one, leaving behind dead worlds in a dark, cold, empty universe. This is heat death. It's also unlikely to happen, at least according to physicists. See, dark energy doesn't have to get stronger. It could stay the same, or even get weaker. If that happens, then gravity will eventually win, pulling everything in the observable universe into a single, gigantic black hole. And if that happens, we won't notice. That's because at the end of the big crunch, all the matter in the universe will eventually be inside the event horizon of that final black hole. Nothing, not even light, can escape a black hole's gravitational pull. That means no signals will be able to reach us from beyond the event horizon. Basically, we would see the universe end right here on Earth, as everything got sucked into that final black hole. It would be pretty hard to imagine it happening because no light would be able to escape the collapsing universe to reach us. But maybe we see one last supernova as all the stars in the night sky go out one by one, leaving us in total darkness. Or maybe we'll see nothing at all. While scientists were busy working out equations, the public imagination took a more immediate vision of cosmic doom. The Cold War brought with it the fear of nuclear apocalypse, often framed as the end of the world. Asteroids, alien invasions, rogue black holes. These became the stuff of blockbuster movies and doomsday prepper manuals. More recently, the Mayan calendar myth predicted that the world would end in 2012. None of these predictions came true. But that hasn't stopped us from worrying about the end of the world. After all, it's been a staple of human storytelling since the dawn of civilization. But today we have a new story to tell. Modern cosmology is more precise than ever before. We can describe the end of the universe not in myths, but in mathematics and physics. What's more, our scientific doomsday stories still seek meaning in an ending. The heat death, when the universe is a cold, dark void, resembles ancient visions of eternal stillness or night. The Big Crunch, where everything is destroyed in a collapsing galaxy, echoes cyclical myths of destruction and rebirth. And the Big Rip, where the universe is torn apart by the accelerating expansion, mirrors apocalyptic visions of sudden and violent catastrophe. The difference is that science doesn't need gods to tell these stories. It uses data, the expansion of galaxies, the cooling of stars, the behavior of dark energy. In other words, where myth once used gods, science uses data, but both speak to the same human need to understand how everything ends. And here we must make a crucial distinction. While stories about the heat death, the Big Crunch, or the Big Rip may sound terrifying, they don't actually describe the end of the physical universe. They describe the end of our ability to observe the universe. They're the end of the story from our perspective, not the perspective of the universe itself. Because there will always be places in the universe that are hot, or dense, or expanding, even as our local region becomes cold and dark and empty. The laws of physics may change, but they won't end. Furthermore, we are the first generation of life on Earth to scientifically calculate the end of the universe. We can trace stellar life cycles. We can measure the expansion of the cosmos. We can even simulate the far future with supercomputers. We know our sun's timetable. We know the timescales of stars and galaxies. This gives us not only knowledge, but responsibility. Life knows the first time in cosmic history, life knows the limits of its environment. Hi, this is someone from my channel. I'm here because we've just wrapped up our series on the heat death of the universe. You've heard some really great reactions to the project from viewers like you. They're saying things like, mind-blowing, absolutely amazing, extremely well done. But one viewer was not convinced. He said, I don't believe anything in this video. Well, I'm here to tell you that we made sure to get this right. We checked and double-checked everything. We interviewed experts, we read papers, we looked at studies. We wanted to get everything as accurate as possible. It's our pledge to you. But of course, we can't please everyone. So let me ask you, what do you think? What did you learn? Do you have questions? Let me know in the comments. And hey, if you're not already subscribed, come on, hit that button. Now back to the video. This is the story so far. Once upon a time, there was a Big Bang. Then came the first atoms, the first stars. Then solar systems formed and planets cooled, some suitable for life, others not. 4.5 billion years ago, life arrived on Earth. For most of history, the planet was a quiet backwater. But over billions of years, creatures grew larger, smarter, hungrier. About 300,000 years ago, humans arose, followed soon after by our closest relative. Homo sapiens, uniquely self-aware, we peered at the stars and wondered if we were alone. We explored our home planet from pole to pole, discovering both its wonders and its fragility. And then we reached out beyond our cradle, venturing into space. Our species has barely begun to explore the galaxy, let alone the universe. But we are driven by nature's oldest urges to survive, to grow, to overcome, to endure. Because as we have seen, our world will change. Our sun will swell and engulf our home planet. But if we prepare, we might survive. We might journey to other worlds or build homes among the stars or discover new sources of energy. Perhaps we will tap the immense power of nearby black holes. We might thrive alongside enigmatic alien beings or rule over countless planets. Maybe we will achieve immortality, uploading our consciousness to vast computer networks, becoming pure thought. All these futures lie ahead, not to mention unimaginable possibilities in other universes. Only the future will tell what path we will take. God. However, lurking in the background is the music of the spheres, a song of gravity, nuclear fusion, expanding space. A song that whispers of an inevitable ending. Even the greatest civilizations must contend with the ultimate question. How long can life last? The answer depends on how we define life. If we mean biological life, then Earth may have already given the answer. Fossils tell us that life arose spontaneously under conditions that haven't existed for billions of years. Yet life found a way. If that happened once, it could happen again and again. Even after the sun grows cold, after the Earth becomes a barren rock, there could be another Big Bang, another chance for life to arise, Of course, this is a long shot. But from the universe's point of view, the odds don't matter. If there is even the tiniest chance of life continuing, then it will continue. Nothing can stop it. But what about civilizations? Could we establish societies that span the universe? Could we master physics and bend the laws of nature to our will? Well, yes, we could. But we need to hurry up. In about 5 billion years, our sun will run out of fuel and expand into a red giant. Our planet will sizzle and burn, baking our oceans, scorching our continents, and blasting away our atmosphere, lest we leave, either by traveling to another system or creating artificial habitats in deep space or on distant planets. We won't last much longer. Sure, we might be able to preserve ourselves for a few million years by suspending animation or uploading our minds to computers. But eventually we'll use up all our resources, and without energy production, our technologies will rust. The dinosaurs didn't leave behind a single skyscraper. We might fare better, but how much better? What if we accelerate the evolution of our own sun? By scooping out its core and squeezing it, we could make the stars shine brighter and hotter, giving us several trillion more years of stable sunlight. But what about the rest of the universe? After all, other stars won't be so lucky. Soon after our sun runs out of hydrogen, most of the Milky Way stars will go supernova. Some planets will be destroyed. Others will be blasted with gamma rays, stripping them of their atmospheres. Most life will die. And in the end, all the stars will go out. Their light will turn into a cold, faint glow. Almost all the atoms in the universe will settle into their lowest energy states. No gradients, no flow, no change. This is the heat death of the universe, the end of all experience, the end of everything. Or maybe not, you see. There's a problem with defining the end of the universe. To do so requires information, the ability to communicate and compute, which itself requires energy. But as the universe reaches heat death, usable energy disappears. So who will be around to measure the end? Will anyone care? But wait, hold on. Perhaps someone or something will. Perhaps intelligence will persist, finding ways to generate small pockets of energy, keeping small parts of the universe alive, at least for themselves. They may not notice the darkness spreading around them, just as today we cannot see the expanding dark void, the eroding black hole horizon, or the region where gravity overwhelms all other forces. Perhaps all those who endure will be swept up into a new era dominated by black holes, an era that lasts for trillions of years. Even the largest black holes will eventually evaporate, sending their mass back into the universe. But by then, all energy differences will be erased. There will be nothing left to organize, nothing left to influence. Intelligence will truly be alone. So this is the end, right? Wrong, even this may not be the end. Mathematicians have pointed out that in an infinitely large space, infinitely large time, certain processes are essentially impossible. Among them, perpetual motion and increasing entropy, the tendency for things to fall apart. In fact, mathematics says that perpetual organization, the opposite of entropy, should be equally impossible. However, living things appear to violate this law. They maintain complex structures despite constant disorder. Physicists have even suggested that life could thrive after heat death. Imagine a universe without energy gradients, but brimming with quantum fluctuations. These tiny variations could be harnessed by highly advanced technology, allowing small pockets of the universe to flourish. Other scientists have proposed that we could escape our dying universe by tunneling into a new one, bringing along whatever we want. Sounds crazy? Maybe it is. But the same thing can be said of the notion that life could somehow slow down time or find loopholes in physics. The fact is, we simply don't know. The most important thing to remember is that the timeline leading to the heat death of the universe is unimaginably vast. In comparison, human civilization is younger than a star. Our species has existed for less than 1/10 of the time since the Big Bang. Moreover, Earth is a mere speck in the vastness of space, one planet around one ordinary star in a galaxy that is neither special nor particularly large. The fact that life arose here and now may be merely a matter of chance, a cosmic coincidence. If so, it's hard to imagine why this particular occurrence would be the last. Even if life fails to endure the heat death, some form of intelligence may persist, tapping the immense power of black holes to keep small parts of the universe running. who are we to say that such an existence is less real or less meaningful than our own? Ultimately, this question may not be answerable until the end of everything, but that doesn't stop us from trying. With each new discovery, we fill in the gaps in our understanding. With each new technological breakthrough, we push back the darkness a little further. And in that endeavor, we are united with all past, present, and future civilizations, all striving to understand the music of the spheres. The fact that so many of us are drawn to this question suggests that it is more than an idle curiosity. To contemplate the fate of everything is to confront our place within it. We are the first witnesses, a nascent intelligence glimpsing not only the past of the universe, but its future as well. We are poised at the very beginning of a timeline that stretches across nearly the entire lifespan of the cosmos. If intelligence endures, our story could stretch across that entire timeline too. And as we peer into the abyss, we see reflected back at us the story of everything. It began in fire, and it may end in ice, collapse, or disintegration. But for now, in this brief moment on Earth, we live in the light of a star, under skies still filled with galaxies, in a universe still young.